So for quite a long time, I mean, we're talking here of 1916. In the early 20s, say about 1922, the problem was resolved. There was nothing really bad happening at r equals 2m, and the way this was shown was by Eddington, an English physicist of the time, mathematician, and he showed that everything was well behaved at r equals 2m. All he did was he changed the coordinates, and he discovered that he could write it as this here, which is just Minkowski space or special relativistic space, plus 2m over r times a perfectly well-behaved expression. This is infinite when r equals 0, but nothing bad is happening at r equals 2m. So the problem was coordinates before. The coordinates were bad, not the metric. Now, what is the interesting thing is that all black holes have this form, and they all have the form Minkowski space, that's just a name for this metric, plus something times the square of a vector. And the only, well, this may be singular, infinite, close to the origin, but it's well behaved elsewhere. Showed that the event horizon is well behaved, but there's still something strange happening, as you probably all know. And what's happening is that you can approach as close as you like to that horizon and still escape if you've got a strong enough engine, but if you cross r equals 2m, you've gone. And the reason is that anything inside r equals 2m, even traveling at the velocity of light, it's falling inwards. So there's no return. So this is the famous surface. Okay. Now, what about the Earth and the Sun? Okay. Can they collapse to black holes? Well, if the Sun was to collapse to a black hole, at the point that it actually got to r equals 2m, if we forget about the spin for a moment, that's the density that it would be. 20 billion, whatever. I'm not sure how many zeros it's got. What about the Earth? Well, that's how dense it has to be. Quite ridiculous. The Sun is its radius would be a kilometre or two. The Earth would be that size. Okay, there's no way that the matter can collapse for either the Sun or for the Earth down to these densities. It was Chandrasekhar who was looking at neutron stars. Now, a neutron star is what's left over after all the energy of a star has been used up. It's mostly neutrons, so it's now realized there's a lot of protons in there too. It's as dead as can be. Chandrasekhar showed that if that neutron star was larger than 4 point something solar masses, the gravitational force would be too strong for it to stop collapsing. And in fact, it would have to collapse right down to a black hole. Okay, but that's 4 point something solar masses. The Sun is not. It's too small to do this. Okay, so it can't happen for the objects we're interested in. Now, that's all very well, but Schwarzschild was looking at a non-rotating body, the simplest possible thing. What people really wanted was a rotating body because everything in the world, in the universe, rotates. it's impossible to be completely stationary. I've tried for years, but I keep moving around. So that meant that physics needed a rotating solution. Okay. It was possible, and most people thought it was true, that a rotating body would not collapse down to a black hole. That the rotation would mean it couldn't get into this small region which inside an event horizon. So also, nobody really believed in black holes because no collapsed objects were known. Nobody had seen anything that could possibly be a black hole. And the whole problem of black holes was pretty much ignored. But nevertheless, people were looking for a rotating Schwarzschild. Should have been simple, after all. Okay, so going forward rather than backward in time, a lot of people worked on it. Okay, in fact, for 40 years, there was a huge amount of work done to try and solve the equations for a rotating body. Now, things were made as simple as possible. The obvious approach was to assume that at least it's rotationally symmetric. So it's like spinning this can. You know, it's allowed to not be a ball, but it's got to be at least symmetric as you in that respect. And then you would let it spin. So any old spinning body would have done. Nobody cared whether it was the shape of this can or an ellipsoid or what it was. They just wanted a solution. Okay, so the equations of the Einstein equations were simplified for a solution which only depended upon two things. The radial distance and the angle there. So that was two coordinates. And one you could call r and the other was an angle. And time, they were looking for something that didn't depend upon time. That would have been too complicated. So the equations were simplified in many ways. A lot of people had formulations, particularly Petru. Got some beautiful, simple-looking equations, but they were non-linear partial differential equations in two variables. And you don't solve non-linear partial differential equations easily. And strangely enough, not a single solution was found for these equations. Okay, there were a lot of beautiful things done with them by Petru, and he showed that if only you could solve them, you could do various things, but couldn't solve them. So what was going to happen? Basically, it turned out from my point of view anyway, that what was needed was an extra assumption. There were too many solutions. These partial differential equations have lots of solutions. We just wanted one, couldn't find one. Needed something extra to put in. So, about this time, 1960, the algebra of the curvature tensor was investigated by Prof. It's like a matrix. You know, those of you who have done advanced algebra, not awfully advanced, will have met matrices, and these are symmetrical objects to two dimensions. The curvature tensor's got 4 indices, not just 2, but it's still an algebraic object. And Petrov looked at all possible types. Now, for a matrix operator, there's certain eigendirections. We're talking algebra here. There's a 4-dimensional matrix will have 4 eigendirections, which satisfied a characteristic equation. These directions are important to the matrix. He managed to get all the possible canonical forms for this curvature tensor, which has got 4 indices. Okay, and what was noticed was that all the known solutions, and what were the known solutions? Schwarzschild, plane-fronted wave, and nothing else. That was it. Of useful solutions, there were only 2. There was a solution which represented a wave going along, plane-fronted, simplest possible wave, and Schwarzschild. So these all had, they had these 4 principal directions, and they tended to repeat in pairs. They weren't all different. So what, you say? I certainly, and I would agree, so what? Well, the known solutions, not just the interesting physical ones, but others, all had this simple property, what was called algebraically special. So around the early 60s, people started looking at the properties of spaces that were algebraically special. Ivor Robinson and Andre Troutman, they managed to find all algebraically special solutions, that's those with this funny property, which had another simplification. They were, and they got some rather nice equations, no physical significance whatsoever. So that was a failure. Okay, our group in Pittsburgh in 62, 63 looked at the general problem and totally stuffed it up. Okay, there's some identities called the Bianchi identities, something like conservation of energy and momentum, but a bit more general. And they calculated, while they were trying to solve the equations, they calculated one of these identities in 2 different ways and got different answers, which meant they'd made some mistake somewhere. Their problem was they didn't realize what they were doing then anyway. So that was a failure. Now, I'd been looking at the problem, but I'd heard that they had solved it. So I hadn't tried to go anywhere with it. Ivor Robinson and Andre Troutman were also trying to solve the general problem and had been for quite a long time, but in the end, they got the answer they were looking for, but there was more to it than just this problem that led to Kerr, so they weren't actually on the way to it. Okay, so we'll forget that. The only reason I mention that is that one of the people involved in that failed attempt has been complaining for years that if only he hadn't made a mistake, he would have found the Kerr solution, and I would say he'd have made some other mistake, but it didn't really matter. In this context, if you win, you win. If you lose, you lose. It's like everything else in life. Okay. So, that wasn't good enough. When I had found the equations that were left over for spaces with this algebraic property, I still had some horrible partial differential equations, horribly nonlinear. They weren't even of the 2nd degree. They involved 3rd derivatives. And furthermore, they're actually inconsistent. So by the time you got rid of the inconsistencies, you could have been up to 5th derivatives. That was useless. It needed something more.